So in this video, we're going to talk about how to read and make very simple plots using so-called triangular or ternary diagrams. And then in a later video, we'll show how you can make these diagrams in Excel. So the first issue with ternary diagrams is that why are they so common? You might ask that. And the reason they are common, at least in the earth sciences and geology especially, is because so many rocks and minerals are made of dominantly two or three kinds of things. So for example, we have this very nice diagram from Dexter Perkins' online mineralogy textbook, and he shows the plagioclase, excuse me, not the plagioclase feldspars, the feldspars generally. The feldspars come in two series, the plagioclase series here, which is a mixture of albite and anorthite, and then the alkali series, which is a mixture of mostly orthoclase and albite. Feldspars can contain many other components. For example, they can contain lithium or strontium or barium. So things like potassium, sodium, and calcium are not the only cations beyond aluminum and silicon that can go into a feldspar. But these components tend to be relatively rare or low in abundance. And so when we talk about a feldspar composition, most of it, 99%, very close to 100%, is going to be the sum of these three components, orthoclase, albite, and anorthite. So even though these fellows might be very important, things like lithium or strontium or barium components in feldspar, if we want to talk about the larger components of a feldspar composition, we can pretty much ignore these. And if we do, if we take all of the feldspar components but ignore all but these three, orthoclase, albite, and anorthite, and let these three sum to 100%, then we could plot them in this kind of ternary diagram. And the way this ternary diagram works is stuff that is made of 100% orthoclase would plot at that apex there, stuff that's 100% anorthite there, and then stuff that is 100% albite there. Now, it's very rare to have actually, you would never find 100% pure albite probably in nature. There's always going to be a little bit of potassium or calcium around that will contaminate it. So if we have some kind of solid solution, we can now contour this diagram, and this is what Dexter Perkins has done very nicely here. So for example, if this is the 100% line here, you can imagine, well, we don't have to imagine, they're shown here. Here's a 90% contour for orthoclase, and then an 80%, and going all the way down to, well, 0% would be down here. So this line here, the albite and anorthite join, would be the case where we have 0% orthoclase. We do the same kind of contouring relative to albite. So here's 100% albite here, and then a 90% contour, an 80% contour, going all the way down to we get to this line here, the orthoclase anorthite join, and that would be a line where we have 0% albite. And then we could do the same kind of contouring here, 100% anorthite, and then 90, 80, 70 until we get to 0% here. So let's plot a couple of points just to give an example. Let's say we have a mineral that is 70% orthoclase and 30% albite. Where would that fall? Well, the sum of this is 100%, and there is no anorthite that's being listed. So if this is a real mineral, it would plot somewhere on this 0% anorthite line, right? So here's 100% anorthite here, 0% would be on this orthoclase albite join here. Something with 30% albite, we could just look at the contours. Here are the contours for albite, 90, 80, 70. We can go out, where is 30? It's unmarked. It is this here. So that would be the 30% contour for albite, and then that will also hit at the 30% the 70% contour for orthoclase. And so this fellow here would be that point right there. Let's take another example. Let's say we have a mineral that is 90% albite and 10% anorthite. Where would that fall? Well, again, we have a sum where we don't have any orthoclase, so we'd be on a 0% contour here, 0% orthoclase. Remember, it's a 100% orthoclase up there at that apex would be 0 down here. So 90% albite would be along that 90% contour, and then the 10% anorthite would be along this contour there. And so we would have this point, we'll draw it in green. Well, looks like it's going to be red instead. It'll be this point right there. So that's this mineral right there. Let's have something that has all three components. Let's say we have something that is 80% albite, 10% anorthite, and 10% orthoclase. Where would this fellow plot? Well, we'll look for the 80% albite contour. That would be this one there. Then we can look for the 10% orthoclase contour. It would be this one here. Those two would intersect at that point there. And as a double check, if this point is really correct, it should also intersect at the 10% anorthite line. And the 10% anorthite line would be this one here. And indeed, that seems to work. So this fellow here would plot right there. And let's do one last example. Let's say we have something where we have 70% albite and 20% orthoclase, and that would leave 10% anorthite if we're going to get something that will sum to 100. Here's the 70% contour for albite. So the 70% contour is right there. Let's draw that in a different color so it shows up a little bit better. So 70% contour for albite, something that lies along that line. The 20% contour for orthoclase is over here. So we should have something there. And as a double check, we can look at the 10% contour for anorthite. And this one we've already started to draw. We drew it in red. We'll draw it again in green. We'll continue the color that we used before. And it hits right where we would expect. So we have this fellow plotting here. So that's how we do plots in a ternary or a triangular diagram. In the next video, we'll show how you can translate this diagram into an XY plot in Excel.